All right, ready? I posted the homework 4 solutions. I'm going to go through those in class today. And I wanted to introduce you to a new data set that your final homework will be based around. Let's see. When is your final exam, or your second exam? Let me check on timing here. This might be something for your exam if we don't have enough time. Second exam is December 4th, so got Thanksgiving this week, and next week is 27th through the 1st, I think. And you got the next one. Okay. So I think what I'll do is not assign it as a homework, but I'll give you a practice problem to do with this data set that I'm about to show you. That will be a kind of a test run for the second exam. Second exam will be predictive modeling. Okay, so you'll download a data set like this one and either do classification or prediction of a numeric variable. So I'll talk about that a little bit today, and I'll do some review for the exam next week. Yeah. So let me first introduce you to this data set. It's called Happiness. It's up on eCampus now, and the data come from a study called the World Happiness Report. And what we have is 157 countries, Denmark, Switzerland, Iceland, and so on. First column is country name. And then we have a bunch of variables about basically quality of life. So our goal is going to be predict the overall happiness or quality of life level of a country in terms of some of these variables. First variable that we have is the region. Things like Western Europe, North America, Australia and New Zealand, Latin America, and so on. We have a variable called religion, and this is while most any country has multiple religions that are adhered to by a substantial proportion, this is the single highest proportion of adherence. So not everybody in Denmark is Lutheran, but among those who are religious, the majority claim a Lutheran bent, and so on. We also have a variable for religiousness. So, as you might know, some people kind of identify with a particular religious tradition, but maybe don't take it all that seriously. It's kind of in name only. So we have this variable that is intended to gauge like how strongly do they take it, ranging from low, like Denmark, to high, which includes US. Okay. And then we have some numeric variables. Let me first go to the last one. It's called dystopia residual. This is going to be our response variable. This is a single numeric quantity that quantifies the difference between this country and, quote, dystopia. So utopia would be the ideal setting. Everything's perfect. Dystopia would be the complement of that. Everything's horrible. This is the worst, you could imagine. So a bigger number of dystopia residual means better. You're further away from the worst scenario. We're going to model that as our response. It's a numeric response. So this does not lend itself to a classification problem, but it can be a regression problem. Just to clarify lingo, Predictive modeling is all about modeling a response as a function of predictor variables. And if y is numeric, we're calling this regression. That's what the book calls it, the Introduction to Statistical Learning book. Whereas if y is categorical, we call it classification. Not perfect jargon, because both of those can be regression. If y is binary, for example, like in the Hall of Fame data, you did regression. You did logistic regression. Or you could do logistic regression, in addition to LDA, QDA, which aren't really regression techniques. Any predictive model can be done with a regression framework. But just to clarify, when I say regression in a predictive model setting, when the Introduction to Statistical Learning book says regression, we have in mind a numeric response. So that's where we are here, and you haven't had a problem like this yet. So I want you to get at least one example of doing prediction with a numeric variable. So you have your response, and then we have, in addition to these three categorical variables, we have 6 numeric variables. Let me talk through these briefly. The first column among the numeric variables is called economy, and it's a function of gross domestic product. So bigger numbers indicate greater wealth at the national level. The units of measurement for these variables are irrelevant to us. These have been standardized according to some rules used by the World Happiness Group, the people who did the study. But bigger numbers generally correspond to greater positive quantities of each of these variables. We have economy. We have family. Family is a quantification of how important family relationships are, how they are valued in the country. We have health, which is a function of life expectancy. Bigger numbers mean people live longer. Freedom, which is a quantification of how much personal freedom do you have or feel that you have to pursue your own interests and goals. Trust, and that's with respect to government. How much do you trust your government? Okay. And generosity. How important is it for people in this country to give to other people who maybe are less fortunate than they are? So, let's suppose you have this data set, and it's your job to predict the overall quality dystopia residual number as a function of these predictors. So, you have a scenario that can be formulated as a linear regression model. yi, the dystopia residual for country I, is a linear model. So we'd have an intercept. We could have beta 1 times region. Well, let me leave that out for now. Let me only focus for now on the numeric variables. So we could have beta 1 times economy plus beta 2 times family plus ... beta 6 generosity. Plus random error. That's just a linear regression model. Using the data in the spreadsheet as a training data set, you could fit this model to get beta hats, estimated betas, and then make predictions. So if you fit the model to your training data, you have betas with hats on top. You could make predictions. So a prediction in a linear regression model would be yi with a hat on top. For a particular country, I estimate its response by plugging in its covariate values to my fitted model. So you could use the training data, fit the model, make predictions, and then accuracy of your model could be measured with, say, mean squared error. If we used all the training data, this would be 1 over n times the sum from I equal 1 to n of truth minus prediction squared. Okay. So there are a variety of ways to go about doing this exercise, building the model. One way that's semi-sophisticated that we've learned about is a regularized regression model. So something like lasso. You could fit lasso to these data. And remember what that would do is give you beta hat estimates subject to a penalty on how big the magnitude of the betas are allowed to be. Remember that regularized regression, shrunken coefficients, are about balancing the mean or the bias variance trade-off. Any given predictive model, we can break down into bias and variance. In particular, the MSE of a predictive model. So the MSE of my estimated model is equal to the bias of my model squared plus the variance of my model. And regularized regression is willing to allow for some amount of bias if it comes with a suitably large decrease in the variance. If our goal is to decrease the mean squared error as an overall error measure, then you can imagine it may be in our interest to get slightly biased results if the variation of the method decreases. So let me say something about what I mean by bias and variance. So a predictive model, F hat. Bias speaks to the predictions of F. Do they, on average, equal the truth? So does the expected value of F hat of X equal the true value? Or let me say, not F of X, let's say Y. On average, do my predictions match the truth? Ideally, you would like that out of any predictive model. You don't want to be systematically too high in your predictions or too low. But it's not the end of the world if you're slightly off. Variance has to do with how variable are our predictions. So imagine in each of these cases, what we're trying to speak about is the scenario where you go out and you get a new sample and you build your model and you make predictions. And then you do it again. Go get a new sample, build your model, make predictions. There will be predictions bobbing around. And if you imagine sampling many times, building the model, making a prediction, you could average up the truth compared to the prediction. So imagine that we simulated, or let's say we reproduce the experiment many times. That gives us a new data set from which we get an F hat. And from that, we get predictions. If I have let's say 1,000 baseball players in my data set and I build a model, imagine going and resampling 1,000 players, rebuilding the model, and making new predictions. The question of bias is, from sample to sample, experiment to experiment, how different are the predictions that you get out of your model from the truth? On average, in the long run. The variance is about how variable are your predictions from replication to replication. If I get 1,000 baseball players and I build a model, and my predicted value for a player with 500 home runs and this many hits and so on is equal to maybe a posterior probability of 0.85. If I were to recollect a new sample of 1,000 players, do the whole thing again, and predict for that same set of covariates, maybe it's 0.92. You do it again, you get another posterior probability of 0.78. If you repeatedly do that many times, you'd have a prediction multiple times for the same player. Imagine making a histogram of that. How spread out is that? Is it centered at the truth? And how spread out is it? So when we talk about the bias and variance of a model, we have in mind, if you were to repeat this experiment that gave rise to our data in our model building process, are we correct on average? And how variable are our predictions? The mean squared error, the overall goodness of a regression-based predictive model, is a combination of both of those. So you could just fit a linear regression model to these data and use that as your predictive model. You'd have a certain mean squared error that comes out. You can almost certainly do better in terms of decreasing the mean squared error if you use a regularized regression model. The regularized regression model, if no shrinkage helps at all, will tend to pick no shrinkage, or at least very little shrinkage. But typically, you can increase the accuracy by employing some amount of shrinkage. So something like lasso is an automated routine to fit this model, get you beta hat estimates in such a way that it makes an optimal trade-off between the bias and the variance. And as a result, results in a lower mean squared error than otherwise. I think what I'll do as a test exercise to warm you up for the exam is ask you to build both a linear regression model, just a straight linear regression model, and use the lasso. And I'll get that posted today. So work on that at your leisure. I won't grade that assignment since we don't really have time for you to do a full assignment before the exam. But treat that as a practice run for the second exam. Second exam will be get this data set off eCampus, build this predictive model, maybe do a simple cross-validation, and estimate the accuracy of the model. All right, let me go show you the solutions to the homework. All right, so it's Hall of Fame data, baseball data. Your goal was to use both LDA and QDA for predicting Hall of Fame status. Hall of Fame status, categorical, in this case binary. Note that LDA and QDA aren't restricted to binary response variables. So both of them work for generic categorical variables. If you had 5 classes, you can use LDA or QDA. It's nice and simple when it's a binary case, though. So fitting LDA and QDA to a model is super simple in R because they have a built-in function for each. What was a little bit challenging about this assignment was that in addition to fitting these models, I asked you to, quote, tune them. Remember that any predictive model, at least any that I can think of, there's at least one way to consider tuning it. What I mean by tune is vary some parameter of the prediction algorithm and try to pick the value of that results in the highest accuracy. With LDA and QDA, with a model that's based on Bayes' theorem, the predictions are driven by posterior probabilities. These estimated probabilities that a player is in the Hall of Fame given their predictive variables. By default, any software, R included, is going to make predictions for you, unless you tell them otherwise, by predicting yes if the posterior probability is bigger than 0.5. So if it's more likely, given the data, that you're in the Hall of Fame than that you're not, by default we would predict yes, you're in the Hall of Fame. Sensible strategy to employ by default, but often you can do better by tuning. In this case, you can definitely do better by tuning because of the low proportion of players who are actually in the Hall of Fame. Because there are so few players in the Hall of Fame, the posterior probabilities that you get tend to all be pretty small. So you may end up not predicting Hall of Fame for many players at all. That's why I asked you to tune with respect to the probability threshold, kappa. We're going to predict Hall of Fame if the posterior probability of Hall of Fame is bigger than kappa. By default, kappa is 0.5, but we're going to try different choices. So I asked you to consider this collection of possible thresholds. And how do we do that? One way that we could consider doing this is to take all the training data, fit the LDA model, extract the posterior probabilities, and then compare them to each of those kappas individually. So suppose we were considering kappa equal 0.1. Then I would get my posterior probabilities for each of the players in my training data set, and anybody who had a posterior probability bigger than 0.1, I would predict Hall of Fame. We don't want to do exactly what I just described, though, because that runs the risk of overfitting the training data. I have one training data set, and if you take nothing else away from our predictive modeling coverage, I want you to be comfortable with the idea that you don't tune your model on the training data directly. Because, as we've seen in the book, increasing the complexity of a model will always result in lower error rates, higher accuracy on the training data, to the extent that you can overfit the training data. Your model is overly tuned to the training data. So for this process of tuning, picking which kappa is best, we need to either have a train and test split, where the test set is only used for evaluating the accuracy of the different models, or we need to use something like cross-validation. Cross-validation is used a lot in practice. So that's what you were asked to do here. Leave one out, cross-validation. That means you're going to have a loop, a cross-validation loop. Generally, cross-validation is described as k-fold cross-validation, with typical choices k equal 5, k equal 10. In this case, leave one out is k equal n. That means you're going to break the training data into n separate train test splits. The general result with k-fold cross-validation is that you break the training data into k train test splits. Each split has 1 over k of the data randomly selected to be the test set, and the remaining is training. With leave one out, in the loop, each iteration, a single test observation is set aside, just one. I'll show you my code in just a second. But let me say something briefly about the different choices of cross-validation type. Should you use k equal 5-fold cross-validation or 10-fold or leave one out? The general result is that leave one out cross-validation has lower bias than the others, but higher variability. And the general consensus, I think, is that leave one out cross-validation maybe results in too much variation. If you were to repeat your study, the predictions that you get out after doing leave one out cross-validation will be more variable than if you use something simpler, like k equal 5 or k equal 10. In the Introduction to Statistical Learning book, they recommend as a general technique 5 or 10-fold cross-validation. So if you're out in the real world doing predictive modeling and you need to tune your model, my recommendation as a starting point at least is 5 or 10-fold cross-validation. And I'll probably have you do like 5-fold cross-validation in your practice problem for the exam. So you'll get an opportunity to do that. In the KHAN data, K-H-A-N, one of the example data sets that I have on eCampus and the script that I have, in that I do 5-fold cross-validation. So if we have time, I'll pull that open and show you what I mean. It's the same idea of leave one out, except instead of one test individual, in each iteration it needs to be 20% of the training individuals set aside for testing. So let me show you my code. Read in the data. Extracted the 6 numeric variables we were going to play with. And then here's code for LDA and QDA. I set up my sequence of kappa values to consider. I don't actually have the cross-validation coded up. Let me run this code. So let me get R open here. And load this stuff in. So the code that I have in the solutions is one way to do this. It's kind of a shortcut way that uses the CV argument of LDA and QDA. I asked you, or I told you I preferred that you write your own code for this. So let me write it here in class. Let's get a text editor. get the start of the code here. I'm going to replace this set of code with my own implementation of leave one out cross-validation. So let's say leave one out cross-validation to choose kappa. Cross-validation fundamentally is a loop. So I need a for loop. Let's say for I in 1 to n. N is in row X. 1016 players. What we do for cross-validation inside the loop, we train test split. We make like a temporary train test split. So I have everything organized in this DTA object. I think what I will do is go ahead and pull out the response. The response is DTA $ Hall of Fame. And I'm going to use the standardized versions of my 6 numeric predictor variables. So I have y, which is a vector of 1016 yeses and nos. Are they in the Hall of Fame? And I have x standardized, that is 1016 by 6. Each column is one of our predictor variables. Inside my loop, I need to do first a temporary train test split. So let's say y test is y. I'm going to set aside the ith individual as my testing individual for now. I'm looping over different train test splits. And leave one out cross-validation, your test set is always just one individual. So the response testing is the ith element of y. The collection of predictor variables is the ith row of the standardized numeric variables. And then the training set is everything that remains. So I could say y everything but individual I, and I could say x everything but row I. Let's run this to make sure it's doing what we expect. When you're building loops in R, if you write a complicated loop and you copy and paste it all into R, you get an error. The challenge is, where's the error? where in my loop did something break. So what I will often do is run this for a single case and just look at it to make sure that there's not something strange. So for the first iteration will be I equal 1. In the first loop iteration, we're going to set aside individual 1 for testing. Let's see what happens when I do that. Forgot to define y. So my test individual is a yes. The first player that we set aside is actually in the Hall of Fame. The numeric variables for this individual are those. Then we have the training responses. There's everybody except the first one, so 1,015, and 1,015 by 6. We're probably going to have an issue with the way this is oriented. Whenever we go to LDA, say, and ask it to build a model for us, that's the type of syntax we use. We say LDA, response variable, tilde, and then an expression of the predictor variable separated by pluses. If I'm referring to a data frame, I'm expecting there's a data frame with a column named Hall of Fame, a column named home or hits and home runs and so on. This X train is still a data frame. Let's say class X train. It is, well, it's a matrix, which is okay. I'm a little worried that the test one is not. Okay, so X test, I intended it to be a single row of the big X matrix. So that would be a 1 row by 6 column array. If I try to do this kind of code and pass in as the data argument something that's not a 2-dimensional array, it'll give me an error, I think. So we're probably going to have to force this to be of a 2-dimensional form. One way to do that, FYI, pro tip, let me show you something here. If we have a matrix, let's make it just be the numbers 1 to 9, in row is 3. M is just a 3 by 3 matrix of numbers. So the dimension of M is 3 by 3. It's a 2-dimensional array. If I pull out just one row, let's just pull out the first row and assign it to an object called temp. There's the first row, but temp is not a 1 by 3 2-dimensional array. There is no dimension. That means that it's just a vector. Class temp is integer. Like, that means it's a vector of integers, whereas class M is matrix. What happens to make this result is R, whenever you make an assignment to a variable, if it only has one, if one of the dimensions is only equal to 1, like temp should be 1 by 6. What R does is get rid of that 1, and it just treats it as a 6 vector by default. Sometimes that will cause hiccups in your code. So just be aware, if you have a data frame, a 2-dimensional array of data, and you intend to pull out a subset of it and pass that to another function, be careful that the form, the structure of what you pass on is of the expected type. Otherwise, you can get a mysterious error. So what I would do in this case instead of the way I have it written above, I would say, give me the first row, and here's the pro tip. I tell it, don't drop the single element index. If I say, give me the first row, and drop equals false, what I get back is a two-dimensional array, 1 by 3. So over here, I'm going to do that. Because we're doing leave one out cross-validation, and we're pulling just rows of the X matrix out, every time we do that, it's going to be converted to a vector. I would prefer that it remain as a two-dimensional array, because I want to use this type of syntax to use the LDA and QDA functions. So this is the temporary train test split. From this point, it's as if we have a new training data set. We started with 1,016 players. Inside my CV loop, I've created a subset, a smaller training set. And then the general routine would be to build the predictive models with the current training data. So let me say with current training data. And then we will make predictions on the current testing data, storing accuracies. Building the predictive model with the current training data set. That's the easy part of just using the LDA and QDA functions. So I could say fit LDA is LDA, and my response, my vector of responses for the training data is yTrain. And my predictors are the 6 numeric variables, hits, home runs, and so on, from the training two-dimensional array. So I'm going to say hits, home runs, RBI, average, slugging, on-base percentage. And the data that this comes from is xTrain. Just to make sure that this is going to run like I want it to, let's again run just this code inside the loop. I is still equal to 1. Okay, so here's an error that we have to deal with. The data object has to be a data frame, not a matrix or an array. So that's an easy fix. This and this, these need to be data frames. In R, there is a difference between a matrix and a data frame. A matrix is a two-dimensional array populated by variables that are all of the same class. All integers, all numeric, all character, whatever. You can turn a matrix into a data frame with the data.frame function. So I'm going to wrap these inside data.frame. Let's run this and make sure it is as I expect. Okay, so it works now. We have a fitted object. We have fit the LDA model. That means we have all the parameters of the LDA model estimated. And we can make predictions using the predict function. Predict is a generic method in R. It does different things depending on what type of object you give it. We're going to give it as first argument fit LDA. So FYI, predict, as I said, is generic, which means if you want to know exactly what predict will do on an object of class LDA, if you say question mark predict, it won't help you, not fully. It'll show you the generic help file for the predict method. But this object right here, fit LDA, if you ask for its class is called LDA. And if predict works on a class of object LDA, then there is a help file called predict.lda. So just to be clear, let me show you. Here's the help file for just predict. Generic function, and so the documentation will be very generic. Object is what drives what the predict function actually does. You see down here under the See Also chunk several commonly used specific cases of predict. If you use LM to fit a linear model, there's a predict.lm. There's a predict.glm, and so on. It doesn't list predict.lda. That doesn't mean it doesn't exist. So let's do question mark predict LDA. This is specific to using predict on an LDA object. Classify multivariate observations using LDA. Here's the general usage. We say predict, and the first object is the fitted object, like our fit underscore LDA. The second required argument is called new data, and that's just tell me the predictor variables for the individuals you want predictions for. Whenever we build a predictive model, that means we're putting hats on all the coefficients or parameters that define the model. If you want a prediction, you plug in the predictor variables for the individuals you want to predict for. So here, I'm going to say predict using my fitted LDA object, and new data needs to be my temporary held out test set. Doing cross-validation, we temporarily train test split. We use the temporary training data to build the model, and then we assess its accuracy by applying it to the held out test set. So let's come over to our script and start filling this in. Fit LDA is my object. New data needs to be a data frame, just like we used a data frame here. New data is like data in the LDA call. But again, this needs to be my test sample. So I'm going to say X test. Let's see what else we have. When we're doing LDA and QDA, I don't know that I've emphasized this sufficiently, but it is a version of Bayes' theorem. LDA and QDA are both approximating Bayes' theorem to get posterior probabilities. So if you recall, with training data, LDA and QDA are after this function. What's the probability that y takes a particular value given the data? And according to Bayes' theorem, this is proportional to the likelihood of a particular class times a prior for that class. So we've talked about priors a little bit. Prior is just prior to seeing your training data, prior to even looking at any of your data, what do you think is a reasonable estimate for the overall probability that a randomly selected player gets into the Hall of Fame? When you called LDA, behind the scenes, it made a decision for you what to use for this prior. There are two common choices. Let me pull up the help file for LDA real quick. Here are the arguments for the function. One of the arguments is called prior. We're out of time. These are the prior probabilities of class membership, and by default, it will use the class proportions. So for your training data, what proportion of the players were in the Hall of Fame? Whatever that proportion is, that's my prior probability that a randomly selected player is in the Hall of Fame. You can specify your own prior, though, and that's something you should consider if you're doing predictive modeling. Should you use proportions that reflect your training data, or is there a better choice? If your training data aren't a random selection of all the individuals in the population, maybe, for example, we went and specifically got 500 Hall of Fame players and 500 non-Hall of Fame players, then I wouldn't want to use the class proportions as the priors, because I don't expect half of all players to get into the Hall of Fame. I kind of oversampled the Hall of Fame players. In that case, I may want to specify my own proportions. I think 10% of all players get into the Hall of Fame. So here, I think I'll leave it at default, since this training set is like a random sample from the population, and there's only 10% or so who are in the Hall of Fame. I'll leave that alone. Let me show you one more thing real quick. I know we're out of time. Let's just run this. I fit the data to the current training data, and then I'm going to make predictions on the current test data. The output of the predict function has three elements to it that I can access. The class element is a prediction, and this is the default version of the prediction. If the posterior probability was bigger than 0.5, it's going to predict yes. I also have the posterior probabilities themselves. And it shows me both the posterior probability for no and for yes. For this particular player, the posterior probability of Hall of Fame is near as makes no difference 1. So they were classified as in the Hall of Fame. But in my code, for the purposes of tuning, what I would do is consider all kappa values and store balanced accuracy for each. The posterior probabilities are already computed. They're already right here. So what I would need to do for the different kappas is what proportion for a given kappa, so I could have like a second loop for j in 1 to the length of kappa. Make predictions using that kappa. So predict yes if the posterior probability is bigger than kappa j. And then we would need to record whether our prediction was correct or not. Okay, we are out of time, so I need to wrap it up. But How do you feel about the cross-validation stuff? Did you feel like you were able to implement it? Do you need more instruction on it? How do you feel?
Well, I think I was confident with my answers, but I don't know if this was unique to me, but my code took a while to run.
Yeah.
Is that how it was supposed to be?
Yeah, leave one out cross-validation is going to be kind of computationally intensive because you got to loop over every individual, and then you potentially have to loop over every kappa. So you have a double loop.
It was a nested for loop.
Yep. Nested for loops are rough for R.
I was wondering if I was just like bottlenecked or if there was an easier way to do it.
There is an easier way to do it. You could get away with doing this part without a loop if you wrote your code carefully.
Okay.
But for the purposes of the homework assignment, might as well just do a double loop. It won't take too long. Yes?
Is there a way to like print out percentage of where we're at?
A way to print out percentage what?
Like the current progress, how far we've come.
Sure. Yeah, how do you write a command or a code where it's going to be maybe a long computation time and you want regular feedback about how far along you've gone? You can do something like cat. Cat is just a function for printing something to the console. And every time it sees that command, it prints to the console. So if I had cat I, then in iteration 1, it's going to print 1. And then it'll go off and do the rest of the code here. Once it gets back up to the second iteration, it'll print 2. So you would see on the console 1, pause, 2, pause, and so on. We don't have time for this, but just FYI, there are ways to run R in batch mode, which means you write your R script like this, save it as a .r file, log into a console, like on your Mac, open up the terminal, or on a Linux computer, log into a server, and you can launch this script to be run in R in the background. So if you have a long program to run, you can't leave your computer open for 24 hours. So you can run it in batch mode, close your laptop, or disconnect from the server, and it just keeps running. What I do in cases like that is I have a command like this to write to a text file. So if I have a job running on the servers, it may take a few days to run, but I can log in and look at that text file, and it tells me how far along in the process are you. I'll finish with this tip. If you go to its main homepage, the CRAN website, and if you go to, let's go to the main landing page. If you go to manuals, they have several manuals, and this R extensions is handy. It shows you how to run in batch mode. It also shows you how to dump programs to C or C++. So in nested loops can really bog R down, whereas something like C can do nested loops very quickly. So in professional programming, what we'll typically do is have a wrapper function. Give me your data, I'll do some processing, and then when it's time to do really computationally intensive stuff, I'll call an R function that allows me to send my data to a C program. So if you're doing heavy-duty research with really big data sets, you'll probably need to get comfortable with running in batch mode, submitting jobs to a server, and possibly dumping your code to C or C++. I worked for the company that sells S+. R is a descendant of another language called S, which then became S+. It's a commercial version of R. And my job while I was there as a graduate student was to take algorithms from statistics papers and code them up into S+. And that's what we always did, was take a wrapper function, and for the heavy lifting, put it into C. And it's like 10, 20 times faster. Something like SAS is used by really big companies. It has over R the fact that it's faster with big data sets. R is great for many, many things, but working with really big data sets is not its strength. Python and SAS can run circles around R with nested loops and such. All right, I will let you go. Watch later today. I will post a test exercise that will be intended to prepare you for the second exam. Yeah, and have a good Thanksgiving. Okay, see you Monday.